Hello, dear students. We'll start our lecture by discipline Technological Foundations of Mechanical Engineering. And today is theme 10. Write down to your notes the theme of our lecture, Basics for Designing Machine Fixtures. And write down to your notes the plan of our lecture. 10.1 Purpose and Classification of Technological Fixtures. 10.2 Attachment Fittings of Technological Fixtures. And Fixture Clamping Devices. It's 10.3 Fixture Clamping Devices. Write down to your note the theme and plan of our lecture. And we'll start item 10.1, Purpose and Classification of Technological Fixtures. And what is the fixtures? Fixtures are called auxiliary technological devices used in machining for installing and fixing manufactured parts or tools, guidance tools, etc. So fixtures, it's auxiliary technological devices. The use of fixtures significantly simplifies the work of the worker, increases his productivity, and expands the technological capabilities of the equipment. With the help of fixtures, it is possible to increase the accuracy of processing. Since the workpiece being processed during installation takes a more accurate position in relation to the elements of the technological system. The cost of designing, manufacture, and operating fixtures is from 3 to 7% of the cost of manufactured parts. The use of standard parts and assemblies of fixtures make it possible to reduce the cost of their manufacture and design. Fixtures are classified by technological purpose and degree of specialization. For purposes of attachment for mechanical processing, fixtures are divided into the following groups. For installation and fixing of parts or blanks over pieces. For fixation and fastening of working tool. straight to the tool in the processing process. Detail control. Holding, moving, and tuning always the tuning of your pieces. Machine fixtures are divided into groups according to the types of machines on which they are installed. It's tuning, drilling, milling, etc. Maybe grinding. Please write down to your notes. These groups of fixtures and types of machine fixtures. And we continue the next slide. According to the number of workpieces or tools installed at the same time, they're divided into single and multiplace. According to the degree of specialization, there are universal, specialized or group, and special fixtures. And special fixtures. One more time, universal, specialized, and special fixtures. Universal fixtures. Vices, dividing heads, prisms, cartridges, etc. are used in the manufacture of various types of parts. Specialized or group fixtures are used in the manufacture of the same type of parts of different sizes. Special fixtures are used for processing in one operation or for processing one surface. Please write down to your notes these three types of fixtures according to degree of specialization. Universal fixtures, specialized fixtures, and special fixtures. And here are your questions about item 10.1. You have the question, so we start item 10.2, attachment fittings of technological fixtures. The setting elements of the fixtures serve to give the workpiece the correct position relative to the cutting tool. Consider typical cases of workpiece installation and design features of the installation elements. When installing the workpiece on plane, constant, adjustable, self-aligning supports are used. Those that are supplied. Write down to your notes the examples of fittings of the fixtures that you can see on figure 10.1, especially A, B, and C. You have some minutes to do with it. To do it. And if you finished, we are continue. Please look at the next slide. Permanent supports include different designs of pins and base plates. To install blanks or workpieces on raw surfaces, pins with a spherical or corrugated head are used. The latter are used to install large castings and forgings. Pins with a flat head are designed for installation on a plane machined not lower than RA 2.5 micrometers. Blanks over pieces with cleanly machined base. The surface is mounted on the support plates, like in figure 10.1d. Permanent supports change when worn. Adjustable supports, unlike permanent ones, allow you to periodically change their axial position to compensate for the wear of the contact plane of the supports. In this regard, adjustable supports are mounted in the body of the device by screwing into the body on the thread with the lock nut fixed. The resistance in the body of the fixture are generally arranged according to the 6-point rule. Installation elements used as additional supports to eliminate deformation of the workpiece from the action of cutting forces, clamping forces, or the own weight of the workpiece are performed in the form of self-installing or raised supports. An example of the construction of a self-aligning support is shown in figure 10.2. Workpiece 1 is installed on permanent support pins or plates. However, in order to exclude the deflection of the workpiece, an additional self-adjusting support 3 is used. This support, under the influence of the previously compressed spring 5, is pushed up until it stops in the surface of the workpiece, after which its position is fixed with a screw 4. The cap 2 protects the device from the impact of small chips. For large-sized workpieces, wedge supports are used, which are brought in with are locked by tightening the hand well. Support pins and plates are made of steel 45, U8A 20 or 20X, followed by head treatment to a harness of 5660 HRC and grinding of bearing surfaces to RA 0.63 micrometers or microns. When installing the workpiece on the outer cylindrical surface prisms 2, like in figure 10.3, cartridges and bushings are used. Prisms are usually produced with an angle alpha is equal 90 degrees. For precise installation of the prism on the fixture body, pins 3 are used. Fix in the prism with screws 1. Chucks. Chucks are come 2, 3, and 4 jaw, collect, membrane, and other designs. On figure 10.4 shows the structural diagrams of collet chucks. When clamping the workpiece, the collet is drawn into the conical socket by a draw pipe, like in figure 10.4a, or inserted into the cone, figure 10.4b. Collets are made of U10A steel. Cam and collet chucks simultaneously perform the functions of centering or setting the workpiece and the clamping device. If the basic cylindrical surface of the workpiece is made with a deviation corresponding to 6 or 8 IT grade, then the part can be installed in the sleeve. On figure 10.5 shows the installation of the flange part 1 in the sleeve 2, based on the cylindrical surface and end face. If the workpiece is oriented along two outer cylindrical surfaces, like in figure 10.6, then one surface is based on a prism 7 and the other on self-aligned prism 2. The use of a self-aligning prism is due to the fact that the initial blanks are made with certain deviations of geometrical dimensions. To install the workpiece on the inner cylindrical surface and a plane perpendicular to its axis, fingers and fridge are used. On figure 10.7, A and B shows constants, and in figure 10.7, C and D replaceable fingers. The basing of the workpiece is carried out with a hole on the finger and the end surface of the workpiece on the base plate of the fixture. The base plane of the workpiece must be finished. Write down to your notes. A, B, figures 10.7. When installing the workpiece on two holes, two fingers, 1 and 2, are used, like in figure 10.8. 1 and 2. Fingers 1 and 2. Of which one is cut off as shown in the figure. These cuts compensate for error to delta in the distance between the axes of the workpiece holes to be installed, and at the same time provide minimal angular deviations of the workpiece around the axis of the cylindrical pin. The calculation of the configuration of the cut finger is given in the reference literature. The diameter of the cut finger is performed with a fit in the hole, H7, F7, or H9, D9. A finger with slices is also used when installing the workpiece along one machined hole and a plane parallel to it. In this case, the cuts of the finger compensate for the fluctuations in size A. By design, the mandrels are rigid, figure 10.10, and expandable, figure 10.11. On figure 10.10a shows a cylindrical border of the center type on which the workpiece is mounted with tension under a press, with transition under a press. And in figure 10.10b, mandrel on which the workpiece is installed with clearance, and tightened from the end with a nut. On figure 10.11a shows a collet expanding mandrel. When the nut 5 is rotated, the collet sleeve C, which has 3 cuts, moves on the conical surface of the mandrel 4, centers and clamps the workpiece 2. Nut 1 limits the movement of the collet to the left. Expanding mandrel shows in figure 10.11b, having an elastic sleeve 1. This sleeve bursts from the inside with hydroplastic 2 as a result of tightening the screw 3. Tuning the screw counterclockwise releases the workpiece from the clamping force. The base hole of the workpiece must be machined with deviations of at least the 8th grade. 8 IT grade. Expanding mandrels are also available with 3 crackers expanded by an internal cone with roller, bushing, and other designs. When processing shafts based on center sockets or conical chamfers, centers are taken as setting elements. On figure 10.12a shows the design of a conventional rigid center. In figure 10.12b, installation of the workpiece with a conical chamfer on the cut center. In figure 10.12c, the design of the rotational center. In figure 10.12g, the design of the drive center with small teeth that are capable of transmitting torque by inserting them into the base conical chamfer of the workpiece. This center designs cause locating errors when obtaining axial dimensions due to inaccuracies in the execution of center pockets of base chamfers. For precise installation of the workpiece along the length, the design of the floating front center is used, like in figure 10.12d. When the blank or workpiece is pressed by the rear center, its end rests against the end of the cone bushing installed in the spindle bore, which ensures the constancy of the axial position of the processed batch of workpieces. And before we start 10.3 is fixture clamping devices, I want to show to you some videos about fixtures. And first video. What is a fixture? What is
Metal
a
parts
fixture?
created by casting, forging, or other metallurgical processes often require machining operations prior to being ready for service. The casting in this example is a housing for a worm wheel gear. The example here specifies that a boring operation will be performed. The part must be secured so that no shifting or movement occurs during machining. The process of securing the part is known as fixturing or work holding.
Fixturing or
Clamps,
work holding.
supports, and other components are used to create the overall fixture. This example shows a single housing part on a single fixture. Once fixtured, the boring operation can be completed. Larger setups, such as this square pedestal fixture, are capable of holding multiple parts at the same time and rotating as needed. Naturally, this type of setup is preferable for high-volume operations. Like many processes involved in mechanical engineering, fixturing is an extremely important step that must be performed correctly in order to maximize profits and efficiency.
And the next video about fixtures. What are fixtures and work holding devices for horizontal machining centers?
HMC operations require the workpiece or workpieces to be firmly secured during machining processes. Workpieces are secured using work-holding devices or fixturing devices. The most common work-holding devices are vices and fixtures. Irregular fixtures also will be addressed. The purpose of holding a workpiece is to secure a reliable contact between the workpiece and the locating elements being used. To locate a workpiece is to establish its position in the axis coordinate system, and to ensure that the work-holding devices used can withstand the required cutting forces. Proper location prevents displacement of the workpiece and vibration during machining. It also ensures machining accuracy and the correct position of the workpiece relative to the cutting tool. The workpiece is located on suitable surfaces, edges, or bores. The suitability of the surface depends on the geometry of the part. The workpiece could be located on a flat surface, resting on points, or located using a variety of other requirements, such as a serrated surface for holding rough castings and forgings.
It's jig and fixtures animation.
Let us see the 3D model of a typical jig.
It's a typical jig.
A jig is a metal working tool used to hold the workpiece and to guide the tool during machining operations. Let us see an application of jig in drilling operation. Here, the jig holds the workpiece and also guides the tool to drill in correct position. Leaf jig. Let us see the 3D model of the leaf jig. Leaf jig is an open type jig in which a leaf or a plate is arranged to swing about a hinged point to load and unload the workpiece easily. Vise. Let us see a 3D model of a vise. Vice is a mechanical screw apparatus used for holding or clamping the workpiece. Turning fixture. Face plate is one of the turning fixture. Let us see the 3D model of the face plate and its purpose.
One touch clamps where it can be used in automobiles, industrial machines, office machines, semiconductor parts, audiovisual apparatus. One-touch clamps serve for various applications in machining, assembly, testing, and inspection in different industries. First of them is automobile industry or industrial mechanism. Machines, industrial machines. Five-axis fixtures. It was different types of fixtures. So we continue our presentation. We go back to our presentation and we start item 10.3, fixture clamping devices. Clamping devices are designed to create a reliable contact of the workpiece with the mounting elements of fixtures and prevent possible displacement and vibration of the workpiece during the operation. When designing a clamping device, the required clamping force must first be calculated. To do this, outline the workpiece installation scheme and determine the direction of action of the cutting force and clamping force. Consider all the method for calculating the clamping force for some processing schemes. On figure 10.13 as shows the components P suffix 1 and P suffix 2 of the cutting force. Components P1 is directed against the lower supports. Component P2 tends to move the workpiece. For example, P1, P2. Workpiece shift will be excluded if the inequality P suffix 2 will be less than Q multiplied by F suffix 1 plus Q plus P suffix 1 multiplied by F suffix 2. In this formula 10.1, F suffix 1 and F suffix 2 are the friction coefficients of the workpiece against the clamping and setting elements of the fixture. Please write down to your notes schemes on figure 10.13 and formula 10.1. Write down to your notes these parts of our slide. Entering the safety factor k bigger than 1, more than 1, we find the value of the clamping force. We use formula 10.2. Friction coefficient F can be taken when installing the workpiece on flat supports, 0.16. When installing untreated surfaces on supports with a spherical head, 0.18, 0.3. When installed on supports with a corrugated head, 0.7 or more. The coefficient K depends on the specific conditions of processing and fixing the workpiece and ranges from 1.5 to 8. That is in fairly wide range. A significant influence on the value of the coefficient K is exerted by processing a workpiece with noticeable surface irregularities in the draft mode. Increase in cutting force due to wear of the cutting tool, fluctuations in the developed clamping force, instability of the location of the contact points when installing the workpiece on the slats. Write down to your notes the formula 10.2 and values of the coefficient F, and of course coefficient K. Safety factor, its safety factor K can be from 1.5 to 8. So it was the last slide of our lecture. If you have the questions, please write your question in our Telegram group and in the course resource with into the forum. And our time is finished. The lecture is finished for today. See you next week. Goodbye and have a nice day. Thank you for your attention. Goodbye.